Good evening, Year 10s. I trust you are having an exciting Saturday evening, and there's nothing more that you are doing than checking that YouTube channel to see, is there something else this week for mathematics? I mean, what are we actually going to be doing? Well, here's the news. This week you're doing two things. You're doing an assignment and you're doing some content. The content I've actually already summarised here. If you put it up on the full screen, you might be lucky enough to see not only my beard in HD, but the information that's on the board here. So, up here, you'll see a summary. These are the new objects. These are the objects that you haven't, in theory, done surface area and volume of before Year 10 mathematical methods. They are pyramids, so they're kind of like prisms, except they come to a point at the end. So, the old rectangular prism, except it comes to a point. Cones, which are based on a circle and come up to a point, so they're related to cylinders. So a cylinder, something like that, if it was enclosed at the top, except when we're dealing with cones, they come to a point at the top instead of being the same shape throughout. And the last one, which we haven't even talked about yet, is spheres. Now, I'm sure I can give some great examples of spheres later, but I'm going to leave that for another lesson. So, these are the new objects that you need to be able to calculate the surface area and volume of. So to start with pyramids, we've already done surface area. This is what we did last week. We did surface area last week. So we did surface area of pyramids, where generally we added the area of each side, each face on a pyramid together. We did make some formulas for it if there was a square base, and you can look back on that. But that was the surface area of a pyramid. For a cone, we worked out the formula is pi r squared plus pi r s, where s was the slant height. And, you know, you can also write that as pi r with r plus s in brackets. So we did that last week. Actually, we didn't do surface area spheres last week, did we? That's a whole special section. So what's going to happen this week is this here is lesson 1. The volume of pyramids and the volume of cones. This here is lesson 2, the surface area and volume of spheres. That's about it. If you're comfortable with that, you can probably go away right now and do it yourself. Have I lost anyone? All right, so the main point of what we're going to do today with pyramids and cones is these formulas. The volume of a pyramid is essentially 1/3 of the area of the base times the height. If you're dealing with the square and you used x for the side length of the base, it becomes x squared times height. Essentially, if you think of a rectangular prism, looks a little bit like this, and you had length, width, height, you know the volume of that is simply length, width, height. Well, I'll draw some bits here. If all of a sudden that is a pyramid, so it's coming to a point in the middle, and this is actually going to be really hard to draw on the fly here. So it's got the same base, but instead it comes up to some magical point in the middle of everything. Something like that. Doesn't look quite right, does it? Is it the side over there? No, it's because I need to make that out like that. That needs to go down like that, and that needs to cut across evenly. The line there. There we go. So that looks more like what we're going to get in theory, right? All of a sudden, that is a pyramid instead of a rectangular prism. Now, they've worked out, and there's an activity in the text if you want to look into this a bit further, that essentially the volume of this object is going to be 1/3 of the volume of that object. It's as simple as that. You make it a pyramid so it comes to a point in the middle of everything, so in the middle of the length, in the middle of the width. Essentially you could express it as 1/3 times length, width, height. However, the text goes further than that. The text presents it in this way, and the text presents it in this way. It's assuming that the base is a square, which is a little bit different. This is a more general case. Anyway, the main point, guys, is compared to the prism, if you've got a pyramid, the volume will be 1/3 of what it previously was, okay? That's what you need to know. The same actually follows for cones. So compared to a cylinder, the cylinder here, the volume was pi r squared times the height. I hope you remember that. Now, if we suddenly make that a cone, so like we had above here, it comes to a point in the middle, instead of being the same shape, it's actually 1/3 of that. Again, that relationship holds where if it's a cone, it's 1/3 of the area of the standard prism, right? Same relationship, 1/3 in both cases. Now, this is actually a little bit easier than it looks, despite only being in mathematical methods and not being in general mathematics. It's not too bad. So I'm going to give you first off a moderately easy example, and then I'm going to give you a hard example. So I'm going to take that down. I hope you've found the pause button by now, so you can pause and jot that down. It's not a bad summary of what we're doing this week and what we did last week as well, a section of it. So here we go. So first off, I am going to make you find the volume of a pyramid. So first off, I'm going to give you a pyramid. All right, off to the side here. There we go. Yeah, it's not so easy. All right, now this is the one where we're going to give you everything you need. This is going to be the nice question. So I'm going to make this 3.9 centimeters. I'm going to make this 4.1 centimeters. And the other thing I'm going to give you is perpendicular height. And what does that look like? If that's 3.9, we'll give that 5.3 centimeters. Now, that's all fine and well because you're given the perpendicular height. Now, that's the trick with all the work we're doing today. You need the perpendicular height for this to work. If you put the slant height, like the length of across here of the diagonal, you're not going to get the correct amount. To be, remotely comparable, I mean, if you think about the concept of height in terms of rectangular prism, this was a rectangular prism. Height by its nature is always this perpendicular height here, right? It's just that on the side. That's your perpendicular height. But when you're looking at a pyramid, the perpendicular height is the height from the middle, the absolute center up. Right? You've got to be careful with that. In the harder questions in this section, you're going to find they won't give you that height. They'll give you another height and you'll have to work it out, which is a lot more fun. But putting that aside, this is one where you're given the perpendicular height, so it's a bit gentler to start with. So let's do this. So volume equals, now I pretty well gave you that you could use 1/3 length, width, height. The text will do this sort of thing slightly differently. I'll show you it anyway. From the start, as you can do with all pyramids, you can work out the volume as being 1/3 of the volume of the rectangular prism, right? It's 1/3 length, width, height. It's just 1/3 what it would be if it was a prism. And from there, I can just put in 1/3 times the length of 3.9 times the width of 4.1 times the perpendicular height of 5.3. And then I need a calculator, which, conveniently enough, I have one here. We have our friend, it's the FXJP 900. Very nice. So I can go 1/3 times 3.9 times 4.1 times 5.3. There it is, equals, and there we go, we get the volume. So the volume is 28.2, well, I'll round it to the second decimal place, 25, and it's going to be centimetres cubed because we're dealing in volume now. Well, that's it. So it's as simple as that with a prism, guys. You just need to be able to have the perpendicular height, and as long as you've got the perpendicular height, it's just 1/3 of your old formula for volume of length, width, height. That's it. It's done. The text complicates it slightly. I'll show sort of how they look at it. They use that idea of, well, it's 1/3 of the area of the base times the height. But then straight away they go, well, the area of the base of this object is a rectangle, isn't it? So they go, oh, well, area is length, width. And you end up with the same formula anyway that I used. So my leaning from the start is just, oh, it's going to be 1/3 length, width, height. So that's the first example. The second example I'm going to make a bit annoying for you, which I'm sure you're really, really pleased to hear. So, you know, this is a good point to take a pause and relax because it's, I'm going to be mean to you. All right. So the second big example here will be the volume of a cone. So the cone is going to look like this. Goes to a point, and we're going to give you the distance across the top here. And I'm going to give you the distance along the side here. So I'm going to make it across the top here. It's going to be 3.6 meters, and this along the slant here, it's going to be 5.5 meters. Now, again, this is related to a cylinder. A cone is related to a cylinder. It's essentially 1/3 of the volume of a cylinder. So straight off, you can write, well, volume is going to be 1/3 pi r squared height. Pi r squared height is the volume of a cylinder. It's 1/3 of that. But what I've done to you here is something nasty. Do you know what it is? That height needs to be the perpendicular height, right? Must be perpendicular. So it needs to be at right angles to the top. I haven't given that. I've given you the slant height. I've given you the length along the side. Often, that's all you're going to get. But if you think about that, how are these all related? Here is h, the perpendicular height that I need to put in that formula. Here's s, the slant, and up here, what's that going to be? It's going to be the radius, isn't it? I can work that out as well. If the diameter is 3.6, I'm hoping you'd know that the radius is going to be half of that. So the radius is going to be 1.8. Cool? Now, given I know this and this, how can I find that out? At this point, I'd hope you'd realise that we have a right angle triangle sitting in there. If we're going from the middle down, that's actually a right angle triangle. So what's the rule we use? Whenever we've got two sides of a right angle triangle, we need the third. What do we use? Pythagoras. Okay, so if I was looking at this, purely the Pythagoras situation here, I have a right angle triangle, I have 1.8, I have 5.5, and I want to know the value there, h. So this is going back to year 9 and what we did in term 1, and that is Pythagoras. So using Pythagoras' theorem, we write c squared is a squared plus b squared. The issue here is, are we trying to find c? C is always a hypotenuse. We are not trying to find c. We're trying to find one of the other ones here. So we need to rearrange this so that we can find the shorter side. So if we subtract, it doesn't matter whether I'm after a or b. If I subtract b squared from both sides, I'm going to get a squared is c squared subtract b squared. Right? I've swapped the sides there as well. You've seen that trick before. And I want a, I don't want a squared. The opposite of squaring is square root. So if I square root both sides, I get a is equal to the square root of c squared subtract b squared. From there, the beauty of that expression is I can just put the values in. So a is going to be the square root of c is the hypotenuse, 5.5 squared, subtract 1.8 squared. So a is going to be approximately equal to square root of 5.5 squared, subtract 1.8 squared. Put that in our calculator, gives us about that. So I'm going to take it to 3 decimal places, 4 significant digits, 1, 2, 3, 4 in, and I'll get 5.197. I'm particularly cautious about making that value accurate because I know it's got to plug into here. And if I don't get that value right in here, it's going to all stuff it up, isn't it? Now, all right, so does that make sense? Does it make sense that the perpendicular height would be about 5.2? I'm hoping you'd realise, well, yes, it would make sense because that here on the slant, on the side, is going to be slightly more, isn't it? So it makes sense that the perpendicular height would be, yeah, about 5.2. It makes sense. You can always look back and do a sanity check. If I got a larger amount here than I got here, it would suggest I did something wrong with my Pythagoras. It's good to check these things. Think, does this make sense? All right. Now, look, the whole point of that was we needed the perpendicular height. We've got that now, right? A here, I could well call it H, because that's what we called it in the problem here. It's actually H. We've got H. So we can go back to our original formula. Let's do this. So now I can put the values in. 1/3 times pi times, we've already worked out the radius, 1.8 squared, times the height, which is 5.197. And so the volume is going to be approximately equal to whatever we get when we put that in our calculator. So 1/3 times pi times 1.8 squared times 5.197. So there we go, and equals. And we get a little over 17. So we've got 17.63 meters cubed. Remember, we're dealing in volume now, so it's cubic units, meters cubed. Hopefully I did that right in the last question too. Were you paying attention? All right, so that's it for today, ladies and gentlemen. You need to be able to work out the volume of pyramids and cones. In both cases, they are 1/3 their equivalent prism. So in the case of the cone, it's 1/3 pi r squared height. In the case of pyramids, it's usually 1/3 times length width height. It's 1/3 what the prisms were. Practice it, be comfortable with it. It's not too bad. I can give you some really horrible questions if you want. That was nice. The first obvious step to give harder questions is to involve Pythagoras like this, but there's other possibilities. Have fun. Bye.